All right. So the plan for the final presentations is that they'll be on December 1st and December 3rd as a spillover. In case we can't do everyone on December 1st. All right. So December 1st is a Wednesday, and then December 3rd is, what's actually the official last day of classes. It's a Friday. Okay, so and if you have specific questions about the final presentation or the final report, just ask me after class. All right, today, just as a brief note, last time there was an issue with the squash entanglement proof of invariance under classical communication. I sent out a correction in email. I'm assuming everyone got that. And, it's a pretty relatively straightforward fix. Okay, today we're going to talk about entanglement-assisted classical communication. This is our first communication task over a noisy channel. Okay. And it might seem funny that we're starting with this first rather than communication without entanglement assistance. The reason we're doing it is because this is the one of the most beautiful results in quantum information theory for which we have an actual solution to the problem that can be understood as the quantum analog of Shannon's capacity theorem that we talked about at the beginning of the class. Okay. So what we're going to do today, this is going to be a two-part, this is going to require 2 lectures to talk about it in full. Today we'll talk about an upper bound on the capacity. And we'll prove that the mutual information of a quantum channel is an upper bound on the entanglement-assisted classical capacity. And then in the next lecture, we'll prove that it's actually equal to the entanglement-assisted capacity. Okay. So we're going to begin with the one-shot setting. And this is an approach that we've been adopting throughout the course, where we develop bounds for a single instance of a resource. And then later on, we consider the IID case, independent and identically distributed channels, and multiple uses of it. Okay, so this is useful not only from a practical perspective, but also I think conceptually as well, to separate out the information theory from the asymptotics. Okay, so what does the one-shot setting look like? Here we have Alice, who wants to send a classical message. So the classical message will be some classical state encoded in this register, and it's classical information, so it can be copied. Okay. And before communication begins, similar to the superdense coding protocol, we allow them access to shared entanglement. Okay. And the shared entanglement can be whatever. That's what it's going to. That's how it's going to be in the setting. It can be whatever entanglement they wish to have, as much of it, and we won't be concerned with how much entanglement they're consuming. We just consider it to be a free resource. Okay. So they're allowed to have some entangled state. We're going to call that big psi, and this classical state we'll call phi with a bar on top, and P will signify a probability distribution. We'll write down what it is in a minute. Okay, then Alice does some encoding channel that acts on the classical system and her share of the entanglement. Okay. And then the output of the encoder is a system that's an acceptable input to a quantum channel N. So this N is the resource that's available to them. Okay? That is a quantum channel that connects Alice to Bob. You know, specific example, I believe we talked about previously. We talked about all kinds of examples of channels previously, right? The pure loss channel, erasure channel, depolarizer channel, etc. Okay, so it can be, but this, it can be really whatever. And it can even be a tensor power channel. Okay, that we'll do later, where you're, you know, it's the same channel but used n times in parallel, little n times in parallel. So that we'll do later. Okay, that's just a particular example. And so then this dotted line is like the demarcation between Alice's lab and Bob's lab. And then Bob takes the output of the channel in his share of the entanglement and does a decoder. That outputs a classical register M hat. And the goal is for the final state to be, you know, nearly indistinguishable from the initial state. That's the goal. Superdense coding is a special case of this, right? In superdense coding, this is a maximum entangled Bell state. These are one of 4 classical messages. This is one of 4 Pauli operators. The channel in superdense coding was the identity channel. The decoding was a Bell measurement. Okay? So now we're generalizing all of this in a pretty broad way. So now we're saying, okay, you no longer have a perfect channel, you have a noisy channel. How many messages can you send? Right? How many bits can you send over the channel such that they can be decoded with error probability no larger than some epsilon? Okay, and then the largest number of bits that you can send, subject to a constraint on the error probability, that's called one-shot entanglement-assisted capacity. And what we're going to do is establish an upper bound on that related to hypothesis testing mutual information. Okay. So previously we talked about hypothesis testing relative entropy, and then we'll, from that, construct hypothesis testing mutual information. And then hopefully there'll be enough time, and then we can talk about asymptotics. Okay. So that's the plan for today. Any questions? That was basically the lecture in a nutshell. Now we have to work out some of the details. Okay, so the initial state is a tensor product state. Sorry, where this is going to be a so each message, little m, is drawn from a message set, big M, with probability Tm. And then this other register, M prime, is a perfect copy of what's in M. Okay. So a special case of this is a deterministic distribution, where there's probability 1 for one of the messages and probability 0 elsewhere. So Alice is deterministically sending some message, but there could be some arbitrary probability distribution. Okay. So the encoding and decoding together, along with the channel, lead to a final state. What is that? We'll call it omega. That's the final Greek letter. So it acts on this initial state. Now we're just drawing out the math corresponding to this diagram. There's the encoder, it acts on M prime, A prime, goes to A. Then there's the channel, goes from A to B. And there's the decoder. It's just, these are all channels, right? So then the decoder acts on E prime and B. That goes to M prime. Okay. So that's the final state. The decoder is a measurement channel. Right, it's going from two quantum systems to a classical system, and that's what a measurement channel does. So there's some POVM, all the elements lambda. Summing over little m hat. That's the estimate of the transmitted message. These are the POVM elements. They act on the input of the channel and then output the classical guess of what was the input message. Okay. We can also define for each message an encoding channel. Okay. Previously, we defined an encoder that acts on a classical system and a quantum system, but now we can, let's just do it in the serial time. So we can say that E superscript m, little m, is acting on this quantum system, the share of the entanglement. And we just define it like this. For the fixed classical input, little m, it's this induced channel. So in superdecoding, this is one of the four Pauli operators, right? Little m is going to be 0 through 3, and e to the big M is going to be, sigma 0, sigma 1, sigma 2, sigma 3, the four Pauli operators. Okay. So then, doing so allows us to write the final state omega in a different way. So the final state omega, if we work through all the math and use linearity of channels, etc., this is the this register up here. It's not touched by the encoding, the channel, the decoding. And so this gets tensored with a conditional distribution. Where we're going to define this right now. This is the probability that the decoder outputs m hat when m is input. Okay. So that you can calculate. That's related to the Moore rule. By this, right? So the interpretation here is there's the initial entangled state, the encoder, condition on the choice of little m is the message. That acts, then the channel acts. Then this right, so that makes a state, the state right here before the decoding, condition on a particular choice of the message. Right? And then, this right here is a P over M. I suppose we should write P over M elements. That's the decoding P over M. And so then this is the probability that you decode M hat given the input was M. So what is the error probability when sending message M? Denote it like this. It's just going to be 1 minus the probability of correctly decoding, right? So what is the probability of correctly decoding Q of M given M? So then 1 minus that is the error probability. Okay. So that's the error probability when sending message M. And so that's a key figure of merit for this protocol. I've suppressed the dependence on the encoding, the channel, and the decoding, and the entangled state. In the book, we write all that notation. Okay. All right, and then another key figure of merit is the maximal error probability. That's just exactly, we'll write that as P star. And it's the maximum over all the error probabilities for an individual message. And that also depends on the code. So when I say code, what is it? What are the elements of a code? The choice of the entangled state, the choice of the encoding, and the decoding. That's the code, right? And then that's the channel which we cannot change. So, the things we're allowed to change as users of the channel, the entangled state, the encoder, and the decoder. We don't question how, in this setting, how the entangled state could be prepared in the first place, but that's a legitimate question. But the entanglement-assisted setting, we just assume it's available. All right. So we say that a code is an epsilon code if this is the number of messages and the maximal error probability is no larger than epsilon. Right? Okay, and then the thing that we're going to be upper bounding today is the one-shot capacity. Call it epsilon one-shot entanglement-assisted capacity. And it's defined exactly like what you'd want to do. So we fix an error epsilon. It's a function of epsilon and the channel, right? But I guess the primary focus is on the channel. So that's why I put it as this main argument here. And epsilon is a superscript. I guess to be more proper mathematically, put comma epsilon, but it's fine. Right, and so this is defined simply to be a supremum over all possible codes. All message sets, encoder, decoder, and entangled states. Trying to maximize the number of bits. Number of bits is log base 2 of the number of messages. Subject to the constraint that the maximal error probability is less than epsilon. That's the key operational quantity, and that's what we want to get an upper bound on today. All right, and then later on, we can define asymptotic capacity from this one-shot capacity. So to establish an upper bound, the main idea is going to be to compare the actual protocol to one where we make the substitution of the actual channel with a replacer channel. Using a relative entropy. That's going to be the main idea, right? So what do I mean by this R sigma? R sigma is a channel that traces out the input and replaces with some state sigma d. Okay. So what does that channel look like? It's, it's literally takes the input, throws it away. It's like cutting the wire, right? And replacing it with some other state. So when we do this, it results in a useless channel. That is a completely useless channel for communication, right? And so what we're saying here is this is the actual protocol for the upper bound. We're going to take this channel out and put in this replacer channel. And then we want to compare how well the channel does versus one that is non-signaling or useless for the task. Right? That's the main idea. And then what we will find after a bit of work is this upper bound. The one-shot capacity will be bounded from above by a quantity that we'll call the hypothesis testing mutual information of the channel. Okay, so we'll define that later on, but in words, you take the hypothesis testing relative entropy, compare the first argument will be a state that can be generated by the channel versus one where the channel is a replacer channel instead. Okay, and that gives you a mutual information like quantity. Remember, the mutual information we can write like this. This was a homework exercise. Sorry if it's a bit crammed at the top, but it's relative entropy from the state of interest to a product state. Okay? And then right here, with this sigma b here being minimized, that's like you're taking the B system, tracing it out, and replacing it with sigma b. And so it's like, it's related to this theme of comparing the actual protocol to one where there's a replacer channel. Okay? And so this bound will replace relative entropy with hypothesis testing relative entropy, and they'll have a maximization of our inputs. Okay? So that's the plan. All right. So I think we have to draw this small. Okay, so this is going to be our point of reference to that. All right, so the first thing I want to do is establish a lemma. So without the P there, this will be the state with a uniform distribution. So that's maximally classically correlated state. Just 1 over the number of messages. And these perfectly correlated classical states. Okay. And we're going to use a particular measurement called the comparator test. Okay. So it's a binary measurement, and in some sense, every measurement corresponds to a question that you're asking a quantum system. Okay. And so the question here, you should imagine yourself as like a verifier of the protocol. You're testing whether it's successful. So you do a measurement, and what are you going to ask? Is the input equal to the output? Classical, right? That's the test you would do as a verifier, and that's what this is going to be. So this operator is this is a projection, and it'll give the outcome. Yeah, this corresponds to the outcome. Yes, the input message is equal to the output message. No, it is not. Okay. So now let's suppose that omega is a state the marginal on the M system is equal to the maximally mixed state, the uniform state. Okay. So in this, you should really think in this lemma, you should think that these classical systems have been prepared in this maximally classically correlated state. The protocol happens, it leads to some state omega here. And so this condition is true for this state. Right? Because if you trace over M hat, it traces over all this stuff that's trace preserving. And the reduced state here is maximally mixed. Right? So that's satisfied for the final state of this protocol, and that's how we're going to use this lemma. Right? And furthermore, when you do the comparator test on omega, it succeeds with probability greater than 1 minus epsilon. Okay? So it's pretty intuitive, and you can prove it that, suppose this condition is satisfied, the maximum order probability is less than epsilon. That means your probability of decoding correctly is greater than 1 minus epsilon. And so then it's intuitive that if you do this comparator test, which corresponds to a success probability, it will succeed with probability greater than 1 minus epsilon. So that's the connection to this operation. Okay, so the lemma states that you have all these things, then the number of messages you can send is no larger than hypothesis testing mutual information between M and M prime of the state omega. I'm just going to put some abbreviations. Hypothesis testing mutual information. And how is this defined? It's defined exactly like this. Why don't I just write it here? That's how it's defined for a bipartite state. And I want to put a little reminder of what hypothesis testing mutual information is. We have a state rho and sigma. Sorry, hypothesis testing relative entropy. So it's the minimal type 2 error subject to the constraint that lambda is a measurement operator and the type 1 error is less than epsilon. That's how it's defined. Sorry, it's a little smaller. Right? But that's just a reminder of that quantity we used for Stein's lemma. I think we've used it for other things. Okay. So that's the statement. So this creates like a fundamental link between communication and hypothesis testing. That kind of thing was identified by classical information theory people in like the 1970s, and then like slowly permeated and became a big theme. That's a theme that we're using. Okay, so any questions about the statement of the lemma before we go to prove it? So what is it saying? It's saying this is the main thing we're going to apply, plus data processing and something else, and then that'll give the proof of the upper thing. Okay, but this is going to be like a core lemma plus data processing. So what is it saying? The number of bits you can transmit such that you can decode correctly with probability larger than 1 minus epsilon is no larger than this mutual information like quantity of the final state. Right? The thing is, the capacity is a function exclusively of the channel and the error parameter epsilon. It's not a function of the particular code being used. So this bound right now, well, if we take omega to be this state at the end, the state omega depends on D and E in the entangled state. And so to get a bound on capacity, we have to remove that dependence. Okay, but let's first establish this bound. And the main idea will be to use this so that this is an example of a measurement operator that when acting on the first argument of hypothesis testing relative entropy has success probability greater than 1 minus epsilon. And so then to make this relation, we have to figure out what is the error, what does this quantity look like when we use the replacer channel. Okay. So let's call the state tau m prime. It's essentially a state that you would get by doing what we said earlier. Take the original channel and substitute it with a replacer channel that cuts the wire and replaces with the state. So this state, such a state would have no correlation with the input register. It would be a product state. Right? So this state will have omega as the first factor. It'll be a tensor product state with omega as the first factor and sigma as the second factor, where sigma is some arbitrary state. Okay, and then this is equal to the maximum mixed tensor sigma and prime. And now what we want to do is related to this goal of bounding hypothesis testing relative entropy, figure out what this will evaluate to when the measurement operator is the comparator test and the state is the state that results from a replacer channel. That's the main idea. And what we'll find is what some people call like a guessing bound or guessing value. That if you're trying to, okay, so let's write down what we're going to calculate. This is the probability that the classical value in this register will be equal to the classical value in this register. But guess what? There's no correlation whatsoever. So you would expect that probability to be quite low. And it's going to be the same as random guessing. So if you had no idea what was in this register, which will be the case if this is a replacer channel, then your probability of guessing this value in here will be 1 over the number of messages. No better than random guessing. That's going to be the result. Okay? So let's do the calculation, and we'll see if that's true. Right? This 1 over big M outside. That's going to be the final result. Okay, so now you have identity here in the first factor and a state here in the second factor. If there's identity here, that means this value would be the same as if you did a partial trace over big M. That's another way that we define partial trace. Okay. But if we take a partial trace over big M of the comparator test, we're left with the identity of it. Okay. And then 1 over big M, identity M prime. Sigma M is a state. Okay, so we should clarify that as a state. Trace of a state is 1. So we get 1 over M, consistent with what we said would happen. Okay. So if you cut the wire, then your probability of passing the comparator test is like the worst possible, random guessing. Yeah. The hat, they're the, yeah. We could change the whole lemma to be M prime as M hat. Yeah. Probably should. Okay. So now, how can we use this? That right here. So if we use definitions, how do we write it explicitly so that it's very clear? Log base 2 number of messages is the number of bits you can transmit. I'll rewrite that as negative log 1 over M. Okay. So, all right, and then we just proved that this is the same as negative log base 2 trace IM M prime tau M M prime. Okay, so that's what we just proved, just doing some rewriting. And then this comparator test is a particular choice of a measurement operator for this hypothesis testing relative entropy between omega M prime and tau M prime. Right? So it's a particular choice that satisfies the constraint of being a measurement operator, and that this, when it acts on omega, the probability that it passes the comparator test is greater than 1 minus epsilon. So using definitions, we get this upper bound. All right. That's a key step, right? But it is just using this definition of hypothesis testing relative.
Did we get the 1 minus epsilon? Oh, that's given.
That's given. Yeah, this is all given. And when we're trying to establish an upper bound of capacity, that will be given. We're going to suppose that, you know, we're trying to find an upper bound over all possible protocols that satisfy this constraint. Okay. So, but then using the definition of tau, we can write it like this. And what did we do? We proved this holds for all sigma m prime, right? This line of reasoning for this non-signaling guessing bound, it holds independent of the choice of the state here. Okay, so then the idea is for an upper bound, we're trying to get the tightest upper bound possible. So then that's why we take an infimum over sigma b. This bound holds for all states sigma m prime. So then we can conclude this. But plug it into definitions. This is exactly hypothesis testing mutual information. Okay, so that's an upper bound relating the number of bits to a mutual information like quantity. Okay. Good. Right. So, you know, this is the statement dilemma that we will use to prove this upper bound. Right? You can see it, we're already like converging towards that. Okay. All right. Okay, so to apply this to the one-shot capacity, what is the assumption for an arbitrary m epsilon protocol? It's that this maximal error probability is less than epsilon. Well, this implies that the average probability of error, if you choose a uniform distribution, this will be less than epsilon, right? If the maximal error probability is less than epsilon, then the average error probability will be less than epsilon also. Okay? And then you can prove that this is equivalent to what you get with the comparator test. And here we will use m hat. As Drew said, we probably should simply use m hat the whole time. Okay. Then, you know, my dilemma . we get that log base 2 of m is less than this one. Okay. Now what? The next step is to think about the protocol. This was the final state of the protocol. How do we get register m hat from data processing with the decoding channel? Okay. We proved that hypothesis testing is it obeys a data hypothesis testing relative entropy. It obeys a data processing inequality. Okay. And then similarly, mutual information will obey a data processing inequality with respect to local channels. Okay. Here, the split that we're making, the bipartite split, is between this message register that Alice holds onto and what Bob has at his end. Okay. And then the decoder is a local channel that you from here to here. So let's call this state in the protocol here theta. Then using data processing, we get data processing under local channels. We get this. Right? All right, so that's where we are right now. And now we're getting closer to having something that's a function exclusively of the channel. In this step, we have removed the dependence of the upper bounds on the decoder. Now it only depends on the entangled resource state, the encoder, and the channel. So the next goal is to remove the dependence on these two. Okay.
What's subscript of the
theta? Theta is this, we define this state here to be theta. Yeah. All right, so let's analyze the state theta for a bit. I think we can now remove the proof of the lemma. Right? That's where we are. So theta is this state. Right here, it's on registers M, B, and B prime. So it's going to be channel acting on the output of the encoder. Which acts on this uniform state and the entangled resource. Okay, let's look at the reduced state of registers M and B prime. Look at the reduced state there. By inspecting this diagram, is there something you notice about the correlations between M and B prime of the reduced state on M and B prime? Tensor product, perfect. Yeah, so that's the case. If you trace over B, then it like propagates back, and then these were products to begin with. That's what the diagram looks like. Now we'll do the math. So let's trace it. You know, by definition, it's trace over B, this state. I'll write the whole thing. Now we're going to do exactly what we just said. This is a trace preserving map. The encoder is a trace preserving map, right? So if we trace over B, then that's equivalent to removing this map N. And then that's a trace over A, which is equivalent to tracing over M and A prime. So because this is trace preserving and this is trace preserving, propagates back. Okay. And then now you see I M sensor side B prime. So it's a product state. Good. That's what we need to keep using to proceed with the upper bound. So we can write it, you know, if it's a product state, we can write it as a product of its marginals, theta M, theta B prime. That's how you could define these marginals. Right? That's what they are. This one's maximum mixed. I don't know if that's particularly relevant for what we need to do now. Okay, so let's use the definition of this hypothesis testing mutual information. That's the definition. It involves an enthemum over all these states here. Since it's an enthemum, we can make a particular choice and say, well, we'll choose this state to be theta B prime. We'll choose it to be some state sigma B tensor theta B prime. Okay, so we'll like optimize over a smaller set, so the quantity gets larger. So now we'll take an enthemum over sigma B, same thing. Right? But now we proved that theta M tensor theta B prime is the same as theta M B prime. That's what we just proved. Okay. And then this you can rewrite as hypothesis testing mutual information. Okay, so it's like all we did is we moved B prime to the other side of the mutual information. So it's like saying for this setup, because M and B prime alone are in a product state, in that special case, this mutual information is bounded from above by this one. Okay? And so now it's like you're looking at a mutual information between two systems that are, let's rewrite the diagram. I'm going to write it in a certain way now. So this is the cut that we're looking at. This is the bipartite cut we're looking at. So we're looking at the mutual information between two systems external to the channel, which are correlated with systems fed into the channel. We're looking at the mutual information between those and the channel output. Okay. So remove the dependence of the quantity on the entangled state in the encoder. We're now simply going to optimize over all possible inputs of this form. That's the final bound. Okay, that's the final bound. So take a supremum over all possible inputs. I'm going to call this. It's the state C. Will be defined like this. Okay. This involves an optimization over, this reference system could be arbitrarily large, right? And there's all possible mixed states. Okay, so it's like, we're just saying that this mutual information has to be less than this one when you feed in some rho. Because, if we model these two systems as R, the reference system, and this is A, this is a particular example of a state that you could feed in. So now we're optimizing it. Okay. So there's a question now, is this upper bound actually computable? Right? And can you compute it? We're taking an optimization over all possible references. In this case, we can do the same trick that we did with diamond distance. That was a long time ago. But there, using data processing and Schmidt decomposition and purification, you can, this state you could purify, right? So rho RA can be purified to a psi of R prime, R and A, where R prime purifies R and A. Okay. But now, okay, and then from data processing, space here. So this can be upper bounded by, just rewrite it, rho R A. So we're saying that this can be bounded from above by psi R prime R A. We'll define the extended state as this. Okay. But now this R prime and R, these are systems that purify A. Okay? And they're related by a local isometry to purification where the system S is the same size as the channel input A. Okay? That was something we proved about purifications, that the Schmidt rank is no larger than the minimum of the local dimensions. Okay? And then all purifications are related by isometries acting on the purifying system. That isometry is a local channel. So then, you get this. And then I'll call this state data. That's the final bound. That's computable you can actually show that this can be computed by a semi-definite program. Okay? That's a nice feature of this upper bound. The computational time will be polynomial in the dimension of the channel, the dimension of the input and output of the channel. So, you know, it's not efficient in terms of the number of qubits, but in terms of the dimension. Okay. So this quantity right here is what we define to be, you know, the mutual information of the channel. The hypothesis that's the mutual information. Right? It's a function exclusively of the channel and the parameter epsilon. So, you know, we have now proved the main claim at the beginning of the lecture, right? So let's recap the steps. You can see them here on the board, right? This is an arbitrary entanglement-assisted protocol for classical communication over a quantum channel. We assume that we have a protocol where the error probability is no larger than epsilon. Okay? Under that assumption, we proved that the number of bits that can be communicated using this channel and the protocol is no larger than this, I'll just call it mutual information of the input and the output. Okay. We then use data processing to say that, well, we can remove the dependence of the upper bound of the decoder by like propagating backwards to the protocol and saying that this mutual information cannot be larger than this one. Then we use the structure of the protocol such that the state at this time point in the protocol, the state on the systems M and B prime is a product state. So that allowed us to get from here to here. You know, this was a bunch of math steps, but conceptually it took us from here to here. What did that do? You know, at this point it made, this was the mutual information between the message and the channel output and the Bob share of the entangled state. What we really want is a mutual information between something and the output of the channel. So that's what this stuff got us to. So now we're then looking at a mutual information between two systems external to the channel, correlated with what's going into the channel. And then we said, okay, well, now we'll just take a supremum over all such states. And that was essentially the final thing. And then we used some purification tricks like we did with diamond distance to say that that final upper bound can be more, is actually computable because this reference system need only be as large as the channel input system. Once we have that, that's the final bound. Okay, yeah.
Something kind of technical about it is we interchange the
Uh-huh.
I'm guessing that's okay because of the types of
Yeah.
interactions we're getting.
That's right. I could have just put infima here.
Right. But for-
All the infima can be replaced with minimum in this
but for-
development.
but for the supremum, is it-
Oh, this can be replaced with a maximum as well.
Okay, so the maximum does exist in the set?
Yes, yes. And that is related to what we're just saying. This reference system need only be as large as the channel input system. And you know, things like the set of density operators is compact. Okay, because we're dealing with finite dimensions.
So if we were doing bosonic systems, then we would need to keep.
We're doing bosonic systems, we need to keep all that stuff. Yeah. But if you do things like you place an energy constraint in the input, then you turn the set of bosonic states into a compact set. Okay, so that's the key one-shot bound. And let's now move on to asymptotics. About 10 minutes. Okay, we can summarize everything that we did as claimed at the beginning. One-shot capacity is less than mutual information of the channel, which is defined. Yes. Okay. And what's nice with this upper bound is you see the main concept in the mathematical quantity. This is like what goes on in the actual protocol. This is what goes on in the useless one, where the channel traces out system A and replaces with some state sigma B. The infimum is there to get the tightest possible upper bound. The supremum is there to remove the dependence on any possible encoding and entangled state. Okay. So we can now get some other one-shot bounds. Remember this one? We used it in Stein's one. We never proved it, but the proof is in the book. Right? This holds for all alpha 1, epsilon between 0 and 1. So then this implies this bound. Why is that? We're just, this quantity is defined exactly like this, but replace dh epsilon with sandwich range relative entropy. Right? So you substitute it here, you get this. This leads to a strong converse for entanglement-assisted capacity. Okay? We get what's called the weak converse bound. There's another inequality like this that we never proved, but it's actually straightforward to get from data processing. You can relate hypothesis testing relative entropy to the usual relative entropy. This is the binary entropy. Right? So binary entropy defined like this. And yeah, it looks like this. Concave. Oh. Okay, so you can use this bound substitute to get a weak converse bound or one-shot entanglement-assisted capacity. Just substitute in. In our case, this sigma is a state, and trace of a state is 1, log of that 0. To get these bounds, these are one-shot bounds. Okay. Let's now do asymptotics for about 5 minutes. Maybe we can do it. So the asymptotic entanglement-assisted capacity is defined like this. Take the original channel, little n copies of it, divided by n. So then, this one-shot capacity, the units are bits, right? So now we're doing bits per channel use. That's a rate. And then we take the limit as n goes to infinity, and as epsilon goes to 0. That's the asymptotic capacity. All right. These bounds here can be used to show that the mutual information of the channel is the bounds on the one-shot, on the asymptotic capacity. Right? Just quickly as a reminder, how do you interpret this? This is the largest rate at which bits can be communicated in the limit where many channel uses are allowed, such that the error probability tends to 0. That's what that means. Okay. And so now let's do this one. Let's just establish an upper bound on this weak converse, on this capacity, on this entanglement-assisted capacity, what we call the weak converse bound. So how do we do it? Just use this upper bound. Okay. Suppose we knew that this mutual information of a channel is additive. It's like entropy is an additive function of tensor product states. Suppose this is an additive function of tensor power channels. If that's true, then that's essentially the end of it. Because this will reduce to this. Then, if you take limit this term with the independence goes away, you're left with one less epsilon. Fine. And then if you take the infimum over epsilon between 0 and 1, the infimum is achieved in the limit as epsilon goes to 0. And then that gives you the capacity up and down. Okay. So that's the converse part of the quantum generalization of Shannon's famous theorem. This was proved in a very different way by Charles Bennett, one of the co-founders of teleportation, Peter Shor, of course, factoring algorithm, John Smolin, who invented entanglement theory, and the other one's name is Ashish Thaplia. Okay, so for about 2 minutes, let's try to prove the additivity. I'll try to justify it to you quickly. So suppose that we knew that this holds for 2 arbitrary channels. This additivity holds. Right? And you can use this in an inductive argument to get this additivity here. How do you do it? You choose M should be big N tensor little n minus 1. Keep applying this, and then you'll forget this. Okay? So let's prove this one. This inequality is somehow the more trivial of the, so it's a proof inequality, to prove an equality. You can do it in terms of two inequalities. Okay? So this inequality is somehow trivial. And it amounts to the fact that you can choose, to compute this mutual information, you have to optimize your input states, and you can choose them to be a tensor product, and then you'll get this and use the fact that mutual information is additive for tensor product states. You get that inequality. So the less trivial one is the other side. I'll just write somehow trivial. Okay. The other one, to prove it, we have to look at this one, supremum over psi r a1, a2. Mutual information between R and B1 and B2. And the state omega is defined like this. Okay, so how are we going to do it? We're going to use the chain rule. And then it'll be straightforward. Okay, so we're going to do it up here. Chain rule. First step. So look at the correlations between R and B1 and B2, build them up one at a time. So first we have the correlations between R and B1, plus the correlations between R and B2 given B1. That's the chain rule. Okay. This right here is the mutual information between a reference system. Okay. A picture is helpful for this. This is the kind of diagram we're considering for this additivity question. Okay. So, the mutual information of these two channels is mutual information between this reference and these two Bob systems. Okay. Now, using the chain rule, we can say, well, this mutual information is equal to this mutual information plus a conditional mutual information. Okay. Using the chain rule or conditional mutual information, you can bring this B1 over to R, similar to what we did in the converse. So now what are we looking at? We're looking at a mutual information between R and B1 without M in there. That's going to be bounded from above by the mutual information of channel M, the first channel, right? By definition. Next, we're looking at a mutual information between R and B1 and B2. With that mutual information, you optimize over all states with external reference systems. So it's like you group these together, and you're looking at the mutual information between these two, external to the channel and the output of the channel. That's bounded from above by the mutual information of that channel. So we got the additivity. So that's the proof of then you get the asymptotic capacity. All right, we're pretty much over time. Final thing that I'll say is to get a strong converse bound. Much more challenging is to prove this additivity. And, but once you have that, you can combine with this bound to get a bound on the strong converse capacity. To prove that the mutual information is also a strong converse. This is the topic of a paper that Manish Gupta and I wrote back in 2013 and published in Communications in Mathematical Physics. So, and we give the full proof in like appendices and whatever, the chapter on entanglement-assisted communication. But it's possible to have this strengthened form of additivity for sandwich random mutual information. All right. So that's it for this time. Next time we will prove this. So then, obviously, what that does is one of the key theorems of quantum information theory. The entanglement-assisted capacity is equal to the mutual information of the channel. And that is like, you know, the most beautiful generalization of Shannon's theorem. And then everything else is kind of a big mess from this point. Yeah. This can be efficiently computed, the mutual information of the channel. There's algorithms now to officially compute that, so that's nice. Okay, so see you on Wednesday. If there are any questions, feel free to ask. We can keep chatting. Well, sorry. I will not, sorry. You can email me. I can try to answer. Okay, see you Wednesday.
Thank you.
So well.